Hello! So, in this video, we're going to be talking about a little bit more about linear systems of equations, and more specifically, we're going to be talking about this thing called homogeneous system. Now, let me just run you through what I've got written down here, because I think I wrote it down slightly different last time. I think last time I wrote it with two variables, x and y, just to kind of demonstrate the case, demonstrate my point. It's a nice introduction. Well, now I'm going to be talking in the general case. So in general, we're going to have n different variables, but it's kind of, we will keep referring back to, say, a case with two variables, three variables, just to kind of hopefully make things a little bit clearer. Okay, so we've got n different variables, and look how I've denoted them. I've noted each variable with this little subscript. So my first variable is x subscript 1. My second variable is f subscript 2. The reason why it's sort of more convenient for this notation, just a very quick sort of reason, is because, well, okay, we've got 26 letters. Right? Yeah, we've got Greek letters and different letters from different parts of different alphabets. But in general, we've got 26 letters. Well, if we've got 27 variables, then we're stuck. Yeah, because then we're going to have to be a little bit more creative. And that's not including the fact that actually we've already got letters denoting coefficients and constants and our derivatives with respect to time. We've got lots of letters going on. So it actually makes more sense to denote our variables in this case. Okay. Now, if you can remember, just kind of a quick reminder that last time we got this system. What does this system actually mean? Well, it means it's kind of a description of how each variable is changing over time. Okay. If you sort of, I'll just kind of very quickly give a recap. Basically, the idea is with an ODE, when we say we want to find a solution of an equation, is we start off. Well, if we just think of it like this. So we start off with a graph, okay, which is describing how x changes with respect to y, and that's going to be equal to some function, okay, and that's effectively our solution. That's the thing which we want to find from our system, okay, except this is a two-dimensional case, right? So x and y. So our system would be something like dx by dt and dy by dt, and a description of how each variable changes over time. So, for example, let's look at what happens as we go through time. So imagine if we just, as we're going through time, we're travelling along this curve. Okay, we're travelling along this curve. Okay, and as we go through time, we're just looking and seeing how our x variable changes. Okay, well, if our x variable changes, sort of we're travelling along at a constant rate, constant times, if our variable changes in a linear way, this is kind of what we're looking at. It can change in the linear way and non-linear case. We're looking at just the linear case. So we're looking at the way that, the case when our variable changes in a linear fashion. Okay, so that's just going to be equal to some function. Right? And likewise, we can do the same thing for y. So as we travel along this curve, we're just seeing how quickly our y variable changes over time. And likewise, if that's linear, then that's great. That's what we're trying to do. So essentially, what we're trying to do with these kind of linear and non-linear cases is, instead of starting with the graph and then describing how each variable changes over time, we're starting with a description of how each variable changes with respect to time and trying to find how that graph looks like. Okay, and that graph is what's known as a solution. Okay, so that's a really good thing to keep in your head. Right? So we've essentially got this system of equations, and remember, we can condense, because this could be an absolutely massive system of equations. If we've got loads and loads of variables, it can be an absolutely massive system. We can condense this down nicely just by writing all of our variables in one nice little list. This is what's going on here, and we can also write all our coefficients in this nice little table here, and all our constants that kind of tag along at the end in a nice little vector here, and then we can condense it down into something which looks like this. Okay, dx by dt equals ax plus k. All right. Well, this is actually what's known as a non-homogeneous case, and I'm going to come on to what that actually means in just a second. But if you remember, this is, we can simplify this even further by making a transformation. If you like, if we can find an equilibrium point, we can actually move our equilibrium point to be at 0, 0, because that will basically get rid of that constant term at the end. So all of these constants that tag along the end, we can get rid of that if it's at the equilibrium point. It's a bit like if we have a graph. If you have a graph looking like this, okay. Let's have a linear graph. Well, y equals mx plus c describes a linear graph, okay? Well, this c at the end, describes where it crosses the y-axis, right? Well, if it crosses at 0, therefore the c is just going to be 0, so the c sort of very essentially just vanishes, and we just end up with y equals mx, okay? No plus c, because it's just going to 0. So that's essentially what we're doing here. But we actually call this the homogeneous case. So in other words, where there's no constants hanging around at the end. So in other words, once we made the translation, the constants effectively go away, and we call that a homogeneous case. Why do we call that homogeneous and that non-homogeneous? Let's just get rid of this. why should that be called homogeneous and non-homogeneous? Because, excuse me, that may not be necessarily that obvious, right? Because if you think back to when you first met the idea of homogeneous and non-homogeneous, that was right back at the beginning of the course, or hopefully you met it a little bit before that, first year of university, maybe further calculus, or even at further maths. Homogeneous and non-homogeneous. Well, homogeneous just means that the right-hand side is equal to 0. So in other words, we have a system or a differential equation. Let's say y, and so let's say y. Sorry, let's say y, and we have the second derivative of y plus some constant times the first derivative of y plus another constant times just y itself. So y is just a function. Okay, and that's going to be equal to something. Let's just say that's going to be equal to some function, say, on the right-hand side in terms of x. So let's say y is a function in terms of x, and we set up a differential equation, and the right-hand side is going to be going to be some function in terms of x, and we call that non-homogeneous. Well, if this right-hand side was just equal to 0, so in other words, the right-hand side, was just equal to 0. And notice as well what we had before. We had g of x. G of x. Well, how can you spot whether this is homogeneous or non-homogeneous? Basically, the first thing you have to do is get everything involving your function and its derivatives on one side, and everything not involving its function or derivatives on the other side. So look, this is exactly what we've got here. This is the form which we've got here. We've got the function, y. Maybe I should just write that as y, because that looks a little bit like a g. That's a y, okay, plus a derivative of y plus the second derivative of y. So the function and its derivatives on one side, and everything not involving the function or derivatives on the other side. So this is just a function in terms of x, okay? So it's not y, okay? And so yeah, this is what's known as non-homogeneous. Well, if this right-hand side doesn't have a function on the right-hand side which is involving x, if it's just 0, we call that homogeneous, right? So that should just hopefully be a little bit of a reminder. But look, that makes sense with what we've got here, why this should be called non-homogeneous and this should be called homogeneous. Because look, if I just write dx by dt as just x dot, right? Just for convenience, remember that we can write dx by dt as just x dot, right? Because it's anything with respect to time, just for convenience. Oops. Anything with respect to time, just for convenience, we can just write with a dot over the top, okay? Because we often differentiate things, see how things change over time, right? So just dx by dt. So let's just do a little bit of rearranging. Let's move this ax over to the left, okay? So we get minus ax, and then we just leave the k on the right? So basically, this is kind of the form which I've got up here, because we've got x, which is our variables, okay? It's a bit like our function y, and we've got the derivative as well, which is a bit like our derivative of y. Okay, and we've said that it's equal to k, so it's not equal to 0. Okay, so therefore that should be non-homogeneous. Let's look at this case. We've still got x dot, that's dx by dt. Let's move the ax onto the other side. So we've got if you like, the function, which is effectively just our variable vector, okay, and its derivative on the left-hand side. And the right-hand side, well, look, because we've taken this over to the left-hand side, this ax over to the left-hand side, we're just left with 0 on the right-hand side. Okay, so that's why it's called homogeneous, and this is called non-homogeneous. Okay. So hopefully that makes a little bit of sense. Right, now if we go back to what I said before with the idea of solutions, what we basically want to do is try and reduce this system. We want to try and reduce this system down to kind of a solution. So basically what our graph would look like. Because this is currently describing how each variable changes over time. So we want to use that description, we want to use that information to kind of deduce what the graph is actually going to look like. Of course, it's an n-dimensional case, so trying to visualise it as a graph is quite difficult, because we've only really got 3, maybe 4 dimensions if you're a bit imaginative available to us. So kind of 100 dimensions is quite difficult to visualise, but it can be done. Okay. So let's say that, we have dx1 by dt, okay, and that's equal to some linear function, okay, and let's say we're just able to solve that. Okay, so this is the homogeneous case. It's the homogeneous case. So in other words, we haven't got these constants hanging around at the end. So it's just simply dx1 by dt, just in terms of the variables, no constants hanging around at the end. Right? Let's say we can solve this using one of the techniques which we've learned earlier in the course. Let's say that we can solve this. Well, the solution will just be given as x1, okay, and it will just be given in terms of t. Right? So x1 in terms of t, and that will just be equal to something else. Maybe if I show you with a slightly more, sorry, that's not a vector. Maybe if I show you with a slightly less trivial. So let's say dx by dt equals, I don't know, equals 4x. Okay, well, let's say we can solve that. Well, fairly obviously we can solve that. Okay, fairly obviously we can solve that. How we can solve that? Well, this is basically saying that the derivative with respect to t is 4x. So if we integrate this 4x, then we'll get what x actually is. Okay, because, you know, if you like, this is x. Maybe I should put a t there. Yeah, because that should be t, strictly speaking, because x is a function of t. And then if I differentiate this, I'll get 4t. So in other words, what is that x which I started off with? What's the function I started off with, which I had to differentiate to get 4t? Well, hopefully you can see that it's going to be 2t squared, and then plus any constant which you like. Okay, so I've just literally integrated this side to find out what x was originally. So in other words, x is that. So this is literally what I can do. You know, of course, that's a slightly contrived, simple example. But essentially, if we can solve this ODE and just then we can find a solution. Okay. So this is essentially what I'm saying. You know, we differentiate this x1 with respect to t, and this is what we get. Okay. So what I'm doing is I'm going backwards now. I'm starting with this is what we've got. What was our x1 t start off with? And I can do that for all of mine. So the same thing for x2 for all of my variables. x2, and let's say that was g, so linear function, and I do kind of solve it in some way, and I then get another solution which is x2, and I can keep going. So in general, I've got xn variables, so right the way up to xn. Let's say that's equal to h, and then I can find out what xn is. And it makes sense that this should be a function of t because I'm differentiating with respect to t. If you differentiate something with respect to a variable, it makes sense that your original variable had to have your original function had to have that variable in anyway, because if it didn't, then the original, when you take the derivative of it, it would be 0. Okay, go away and think about that if not. So essentially, what I've got now is I've got a system, or I've got my solutions. Okay, I've got x1 of t, x2 of t, xn of t. So these are all my solutions. Okay, these are all my solutions which I formed. All right, and these are solutions. What are they solutions of? These are solutions of my homogeneous. Of my homogeneous system. Okay, so with no constant in the end. These are all my solutions of this. Well, it makes sense then, because at the moment I've kind of worked it out separately. Okay, I've considered each. Sorry, let me just scroll up again. I'm trying not to scroll up and down too much, but there we go. So what I've basically done is I've looked at each individual equation and I've solved it separately. Okay. Well, look, I've said that I can write this system in one neat little way. So it makes sense then that all of my individual solutions can also be written in kind of one nice, neat, condensed form. Okay, in other words, group them all together. And I can write them as something called a linear equation. Okay, and this is what it's going to look like. So again, I'm using my vector notation. So I take all of my solutions, x1 of t, x2 of t, right the way through to xn of t, and I add them together. But remember that in a linear combination, I can have any multiple of this solution. Any multiple of this solution whatsoever, because if you have a solution, okay, if you just multiply it, all you're basically doing is you're stretching it. Okay, it will still be a solution of your original equation. So in other words, I can also have a multiplier, and I'm just going to call those constant multipliers, denote them by c's. Okay, so hopefully that makes a little bit of sense. Okay, this is what's known as a linear combination, and this is a solution of dx by dt equals ax. Okay, so my solution, it will be given looking like this. Okay, so hopefully you're following me up to now. Okay, well, now what we can do is, okay, so this is pretty much the main bit of the video. This is the main idea of the video going. But we can actually go slightly further and introduce some slightly newer ideas to kind of refine this down a little bit further. If you haven't met linear combination before, this is an example of a linear combination. I'll just quickly talk about this before I talk about the next part. This is an example of what's something called a linear combination. Well, what is a linear combination? Well, it's a combination of variables, okay, of our variables. Okay, so x1, x2, xn, these are solutions in general. So it's a combination of solutions, I should say. But in general, a combination of variables. Okay, it could be vectors as well. So it's a combination of our solutions, all right, arranged in a linear way. So in other words, a linear basically means that you can't raise it to kind of any power. So you can't, for example, square this or cube it or whatever. Okay, it's basically just the solution itself, but you can multiply it and you can add them or subtract them. And that's all you can do with linear functions. You can't do anything more interesting than this. You can add them or you can multiply by a scalar function or subtract them, of course. Okay, so this is all a linear combination basically means. So okay, let's try and kind of do a little bit more refining. Let's kind of, refine this down a little bit. This is fine, okay? If you just understand everything up to now, then that's fine to kind of get you through to the next part of the course. But we can actually refine it a little bit further, and we can actually introduce some quite more interesting bits. Okay, so basically, if each solution, so these are our solutions, x1, x2, and x3, right the way through to xn. I'm dropping the dependence on t because I think that's kind of given. All right, so we've got all our solutions here. Right. Well, if they're if each of these solutions are what's known as linearly independent, then that basically means that we can only write this solution, this general solution, x of t equals c1 x1 t, this linear combination plus c2 plus, etc. This basic linear combination which I've got in this box here, we can only write it in one way. Right, so that's quite a crucial result. But let's just talk a little bit about what linear independence actually means. Because I know we've done it before, and some of you might not have done, but it's always good to kind of go back over things and really kind of enforce them, to try and understand them. So let me just introduce what linearly independent actually means by an example. It kind of makes sense that, the clue is kind of in the name. Before I talk about this, the clue is in the name. Independent basically means that they're totally separate of each other. Okay, and that kind of is true. Well, let me just tell you what linear independent actually means. It basically means that any one of these solutions, so x1, x2, x3, right the way through to xn, any one of these solutions cannot be written in terms of any of the other solutions. So in other words, any one of these solutions cannot be broken down in a way such that it consists of parts of the other solution. Okay, so let me just talk about what it means kind of in the context of an example. So let's say, for example, a person is describing a location. A person is describing a location of somewhere, and they basically say, right, okay, so I'll just draw my compass, because I'm going to be using some compasses just in case. So north, east, south, west. So we're all in the same page now. Right. And a person is describing a place. A person is describing a place. And the person says, right, travel 3 miles north, and 4 miles east. Okay, so 4 miles east, and then you'll get to where you are. So in other words, you start here, you travel 3 miles north and 4 miles east, and you get to where you want to end up. So that's a description of how you can do how you can describe how a place is. And these two vectors, 3 miles north, 4 miles east, these two vectors are linearly independent of each other. Why? Because they cannot be broken up into parts of any of the others. Fairly obviously, 3 miles north is in the north direction. It's going up. All right? 4 miles east is going right. It's in the east direction. It's going right. So you've got one vector. This is a vector because you've got a magnitude, so 3 miles, and a direction, north. These are vectors now. All right? So you've got a vector that are totally independent of each other. They cannot be broken up into parts of the other one. So in other words, this 3 miles north vector is only going up. This 4 miles east vector is going right. So you've got one vector going up and one vector going right. One vector going up, one vector going right. They cannot be broken up into parts of the other vector. Right? Whereas now if you said the place is 3 miles north, 4 miles east, and 5 miles northeast. Now, this is what's known as linearly dependent. Fairly obviously, this is called linearly independent. Because, they can't be broken up into parts of the other vectors. But now this system, because you've added the information that it's 5 miles northeast, right? This is now what's known as linearly dependent. Why? Because look at this 5 miles northeast vector. This is the crucial part. The 5 miles northeast vector is the vector that makes the system linearly dependent. Right? So here you had two vectors, one going 3 miles north, one going 4 miles east. The two vectors were linearly independent of each other because they couldn't be broken up into parts of each other. Now you've got an extra vector. So you've got 3 miles north still, 4 miles east, but now you've got a 5 miles northeast vector. This 5 miles northeast vector makes these three vectors linearly dependent now. Why? Well, because look, this 5 miles, this is the crucial vector that's added that kind of puts the system into a state of linear dependency. Okay, this 5 miles northeast vector can be broken up into a bit of right and a bit of up. Yeah, in actual fact, it's I've chosen this because it's Pythagoras, it's Pythagorean triple. It's actually 4 miles across, 4 across and 3 up. But what I'm basically saying is that this vector, this 5 miles northeast vector, can be broken up into parts of the east vector and parts of the north vector. So in other words, it can be broken up into parts of the other two vector. And because it can be broken up into parts of the other two vector, in other words, it's linearly dependent. It includes parts of the other vectors. All right? So that kind of now makes sense in terms of our example. We've got, say, x1, x2, x3, right the way through to xn. Okay, we've got these solutions. Okay, so we've got solutions of our systems. Well, now, if it's linearly independent, it basically means that any one of these solutions cannot consist of elements or parts of the others. All right. So in other words, what this means is if it was just say if it was just 3 solutions, so if it was a 3-system equation, 3 equations in our system. Okay. So we have 3 systems in our equations. What that means is that when we try and draw our solution, each solution will have its own axis. Okay. So each solution will have its own axis. So let's say this is x1, this is x2. This is x3. Okay, so what I'm basically saying is that it's only 3 system. Well, Rn is 3 if you like. It basically means that each solution will have its own axis. It will lie in its own plane. So in other words, the x1 solution will lie in the forwards and backwards plane, for example. And the x2 solution will lie in the left and right plane. And the x3 solution will lie in the up and down plane. Okay, they're totally independent of each other. Totally independent of each other. Okay, because now let's say, for example, let's take the example, if, say, for example, the x3 vector did something like this. It looks something like this. Well, fairly obviously, it consists of a part of the x2 vector and a part of the x1 vector now. So now the x3 vector, because it can be written in terms of x2 and in terms of a bit of the x1, okay, that means that now our system is linearly dependent. Whereas if it was the case, like I had before, if it's linearly independent, it means that each vector, each solution, has its own plane. It lies in its own plane. It cannot be broken up into elements of the other solutions. Okay, hopefully I've made that clear. So now what we can say is that if we've got a system of equations, so we've got our solution, x of t equals c1 x1 of t plus c2 x2 of t. So we've got our system, just like we had before, plus cn xn of t. Okay, so this is our general solution now. If it's linearly independent, it basically means that each solution cannot be written in terms of the other solution. So in other words, this can only be written in one way. This can only be written in one way. If, say, for example, let's say, for example, x3 could be written, or xn, because that's written down. Xn could be written in terms of x1 and x2. Well, therefore, we can break this xn down into a bit of x1 and a bit of x2, okay? And therefore, we'll just have a bit of x1, then we just add that to x1 and add that bit of x1 to x1 and add that bit of the x2 from xn to x2, okay? And therefore, we change our system of equations. We change our system of equations. Or we change don't change our system of equations. We change this general solution. Yeah, because we're adding a bit more to x1 and adding a bit more to x2. So we can write it like this, or we can break this xn down into and write it in terms of x1 and x2 and add it to x1 and x2. And fairly obviously, we're changing the solution, aren't we? Whereas if the solution is linearly independent, in other words, each solution, we can only write each solution in one way, that means that the only way we can write it is like this. Okay, so we say that this can only be written in one way. So in other words, it's unique. Okay, it's unique if linearly independent. If our system is linear, if our solutions are linearly independent, that basically means that this is unique.